Yeah. Thank you, Enrico and Andrea, for once again inviting me to this OT Day also this year. It's always a pleasure to be back, first in Torino, where I studied, we studied together, Enrico, Andrea, and I, and where also we started working in this field. So it's always a pleasure to be here, and also to meet all of you. Actually, an increasing community this OT Day. It's a great sign. So in my group, we are, as many presentations that you have already seen, we are also very interested in studying motor neurons with these techniques of high-density EMG. And having a look at the program where I was asked to give a talk, I decided to provide you another example of application of these techniques, so a bit different from what you have heard so far. And specifically, I will discuss the way in which we can use these techniques to interface humans with machines. This is a very large field, which is called man-machine interfacing, and it's very important. It's becoming a very in rehabilitation, covers aspects of robot-aided rehabilitation, prosthetics, orthotics, and many other topics. Today I will specifically focus on one of these applications, which is the interfacing of humans with prosthetic devices, so with robotic limbs, and specifically with upper limbs. So I will cover three main topics. First, I will provide you a brief introduction, very general introduction on the challenges of interfacing humans with robots. Then I will provide you examples of classic myocontrol for prosthetics. This is state-of-the-art myocontrol, meaning systems that are in the medical market and they are available for patients. And then finally, I will present you the core of my talk, which is our proposal for having a breakthrough into the interfacing of prosthetics by having actually an interface with the spinal cord, but using the techniques that you have heard about during this day. So starting from a broad introduction and overview of the challenges, when we attach a robotic limb with a user, with a patient, we need, of course, to solve biomechanical problems in the attachment, and these are related to socket design or osseointegration, if we even integrate with the skeletal system. But then we also have to solve a problem of neural interfacing, especially for the upper limb. We need to have the possibility for the user to send commands to the prosthetic limb. And if we think at our ends how sophisticated they are and how many tasks they allow us to do, you can imagine how complex it is to establish this brain neuronal prosthetic interface. Actually, the interface is the main challenge in the field. The neural interface with these systems is the main challenge in the field. So if we look at the robotic side, this is state-of-the-art robotics from KUKA. That's a robotic arm, and this is a commercial video that you can download in YouTube, showing you that the technology in robotics has progressed immensely in the last decade especially. We are able to reproduce with robotic devices natural limb and their function in a way that even surpasses the biological limbs. That is not a main difficulty now. But now, as you have seen in this video, these impressive performances are achieved by autonomous control. That means that robot is working autonomously. It's not connected with a human. There is no human that directly controls the actions. Now I will show you a video of what happens when we take a robotic arm of this type and we try to interface it with the brain of a human. And you will see the difference in performance. So this is a video from Brown University, and it relates to a chip implanted in the brain of this patient who has severe motor impairments. And with the brain activity, the patient is trying to control again a Cook arm, which is very similar to the one you've seen before. Now, this is impressive achievement scientifically, of course, because it's a direct brain interfacing, but if you compare it with what that robot could do when he was working autonomously, you can see that the performance is substantially downscaled. And obviously, what you have seen in this video is not a sufficient performance for persons, for example, with amputees. That's very far from the performance of a natural limb. So the problem in this field is this connection, is to connect the brain of the patient to a robotic limb that is attached to the body of the patient and can be controlled as naturally as a biological limb. So in order to interface the neuromuscular system with robots, we can probe the humans at different levels. We can probe them at the brain level. This is the brain interface that you've just seen in the video before from Brown University. We also work on this type of interfacing, but this type of interfacing is very, very complex because we had difficulties at that level to deciphering the motor intention. We can also address the spinal interfacing, meaning that we can place electrodes in the spinal cord, and we can decode the activity of spinal circuits. We can also interface peripheral nerves by implanting electrodes in peripheral nerves, and ultimately, we can also interface muscles. And interfacing, and the more we go peripherally, the more the biological information about the motor commands becomes easier to interpret because it's biologically decoded. So I will focus in my talk on this level of interfacing, basically from the spinal cord to muscles, and I will not discuss much about the brain interfacing because clinically, at least for upper limb amputation, brain interfacing is not a solution in the short and medium term. While at this level, we have the possibility to have clinically viable solutions in a very short development term. All right, so this leads us to myoelectric control. So myoelectric control is the classic state-of-the-art method that companies use to control upper limb prosthetics. And some myoelectric control systems are on the market for upper limb prosthesis since decades now. And actually the technology of myocontrol for upper limb prosthesis in the market has not changed since decades. What I will show you in this collection of videos is state-of-the-art academic research in myoelectric control. These are our laboratories. This is a patient with a state-of-the-art prosthetic hand. It's a commercial hand called the Michelangelo hand. It allows wrist control, opening and closing, and this is based on EMG, recorded from the stump, one of the best ways to control these hands. So these are algorithms we and other groups developed over the years. They map EMG activity into control of degree of freedom of the prosthesis, and in this way you may achieve a reasonably good control of up to, let's say, 3 degrees of freedom, 3-4 degrees of freedom at most. So that's what we can do with classic myocontrol. These systems are not yet on the market. There are simpler systems on the markets, but they may be in the market in a matter of a few years. They are ready for commercialization. And with this classic myocontrol, you may also then extend the clinical applicability by inserting small capsules that transmit EMG wirelessly. And in this case, you have a complete muscular interface. The subject do not need to replace electrodes. Very robust control. These are IMIS, developed initially, actually, at the Rehabilitation Institute of Chicago many years ago, now commercialized. And these are radiography of a transhumeral amputee at the Medical University of Vienna, with whom we collaborate for the clinical validation of these systems, fully implanted, multi-degree of freedom control gross EMG, meaning that this is interference EMG control. So that's all good, and these advances may provide new devices and probably new generation of prosthetics that will definitely improve the quality of life of patients, but still the long-term dream is very far to be achieved. So this is a graphical rendering. Actually, this is from a scientific paper that a group of us wrote and prepared this graphical illustration to indicate what would be the long-term vision in prosthetics. So what you would really like is to have a full replacement of function of the end. So full dexterity, intuitive control, and basically a limb that can be controlled as natural limbs and can even surpass natural limbs in some functions. So we're very far from this goal. And if you consider a classic myocontrol interface, there is no way that you can achieve this goal. It's theoretically impossible because the neural information is substantially blurred in the interference EMG. So this leads us to the last part of the topics I wanted to discuss with you, which has been a few years ago our proposal to go towards that goal. And our proposal was still to use a muscle interface which is clinically viable, but to use that interface to decode motor neuron activity and actually to decode entire pools of motor neurons in the spinal cord, possibly the full population of motor neurons in the spinal cord, and by having precise information of the activity of on those motor neurons, reproduce with a robotic device the exact movements that an able-bodied human would do. And we have been starting working as a first pioneer group worldwide on this concept, and I will show you some results on this. So the idea, as I said, is that by having access to muscle through the neuromuscular junction, it is theoretically possible to decode information that is coming out from the output layers of the spinal cord. And if you are able to do that, then with a peripheral interface at the muscle level, you actually have a spinal cord interface without having to implant electrodes into the spinal cord itself. So very powerful concept. Another reason why this concept is very powerful with respect, for example, to brain interfacing is that the spinal motor neurons that neurally code the movement are in a very small number with respect to the cortical neurons that generate the movement. So there is a substantial dimensionality reduction in the neural information from the motor cortex to the spinal cord, obviously. And if you think the technology, having a relatively small number of neural cells to decode is a big advantage because you may aim to decode all of them. So if you think a brain interfacing is basically impossible to think that we can interface every single neuron in the motor cortex that is responsible for the movement of the end. But if you go at the spinal cord level, this becomes feasible, meaning the alpha motor neurons controlling the end are not that many. And actually, how many are they? That's an important scientific question. And when we ask ourselves, in order to make the engineering design of this approach, we look at the literature, and there were actually no data on the number of motor neurons controlling a limb, in particular the end. So what we did in a collaboration with the Medical University of Vienna, and these are very new data, actually out in PubMed last week, was to have a cadaveric study. So on 8 cadavers, we actually harvested the nerves from the brachial plexus, the nerves innervating the human arm. And we counted the number of efferent fibers and sensory fibers at different levels along the arm, to have an idea of which is the number of motor neurons actually controlling the arm from proximal to distal. And this turned out to be a very interesting study. So the first result of this study is that, as we could have expected, but now we have the exact proportion, the number of fibers that provide motor information, so that actually control the muscles, is in a very small proportion with respect to the number of sensory fibers. This also tells us how important it is to establish sensory feedback when we develop this kind of technology. So on average, if we look at the full innervation of the arm, the proportion of efferents is around 6% of the fiber. The great majority is sensory fibers. The motor information is really reduced to a very small number of fibers. Then the other interesting thing is that if you count the motor neurons innervating the full intrinsic musculature of the hand, so all the intrinsic muscles of the hand, and imagine how complex are the action of the hand. I mean, 20 plus degrees of freedom. The number of motor neurons that control all those muscles and all those degrees of freedom is less than 2,000. It's a very small number. An amazingly small number if you think of that. So you have less than 2,000 motor neurons that control every single action of intrinsic muscles of the hand. As I say, the 20 plus degrees of freedom. So now this is also interesting, as I said, from the basic scientific point of view, because that number of motor neurons is approximately the same motor neurons that are needed to control a muscle, a single muscle like the biceps brachii. So a large muscle is controlled by the same number of motor neurons as the full intrinsic muscle of the hand. So clearly the number of efferent fibers is not a determinant of the complexity of the action. Actually, it is the ratio between motor and sensory fibers that determines the complexity. That was also a result of this study, which is not relevant at the moment. But at the moment, what is relevant is that we can, from the engineering point of view, reasonably plan to interface every single one of these motor neurons. That is engineeringly possible. And if you are able to interface every single number of those motor neurons, then you can reproduce the exact natural function. Then you have the exact neural code to reproduce the function. So how do we interface those motor neurons? Well, you have heard now for the full morning about high-density EMG. And indeed, this is the way that we also use to record from muscles and then to decompose the signal and to identify motor neurons. And in addition to the surface recording, you can also do it by high-density intramuscular recorders. These are systems that have been developed by our group since quite some years. And these are thin filaments that are inserted into the muscle, and each of these little dots are recording electrodes. So you have an high density of intramuscular electrodes. And in that case, you can we use this system also to look at the future when we develop these techniques as a potential system that can be implanted into humans for high-density decoding of motor neurons and for prosthesis control. At the moment, as you can see, these systems are inserted with a needle, so they are not chronic implants, and we use them in the laboratory, in laboratory condition, but in the future, one can have filaments like this into muscles, transmitting wirelessly to the external environment for controlling external devices. Anyway, once you have this probing of the muscle, either invasive or non-invasively, you have several tens or hundreds of EMG recording points. And as you have heard today, what you can do with these several hundreds of EMG recording points is to decode motor neurons. So you can decompose the signal in a robust way, and you can obtain discharges of activation of individual motor neurons. So this is an example of around 100 motor neurons innervating one of the muscles of the hand, and these have been decoded with recordings that are both invasive and non-invasive. So really hundreds of recording points into the muscle and outside the muscle. And in doing that, this number of motor neurons is basically the full pool of motor neurons controlling that muscle. There are not many more motor neurons active during that task. So that means that when you have the motor nucleus, where the pool of those motor neurons is located, with this information that you get with this type of interfacing, you have a probing and interfacing of the full nucleus where the pool of motor neurons is located. So you have an ideal spinal interface. You would never be able to do that by actually inserting electrodes in the spine, but you can do that with this type of interface. So very, very, very powerful. And you can do it also in less constrained tasks than isometric tasks. So these are examples of wrist flexion extension, and these are motor neurons activated during wrist flexion extension in able volunteers. So now, if you are able to do that kind of decoding, so if you are able to reach the spinal cord, you can reconstruct by the neural information that you get, you can reconstruct the biomechanics of the missing limb, because you have the exact neural information sent by each of those muscle tendon units. And so you can put together a biomechanical model that, having as input the neural information, reconstruct the biomechanics. And if you are able to do that, you can then substitute the degrees of freedom in the biomechanical model into degrees of freedom of a robotic arm. So the concept is this one, and there is one more aspect that is interesting in this approach that I would like to discuss with you. So one of the problems when you interface muscles in this application is that you may have no muscle tissue available, meaning that if the amputation is very high, you may have actually no muscles to interface. And then the problem is, how do you actually get the nerve information if the nerve has been cut and you don't have the muscle from where to record the EMG activity? But then our proposal that comes also from a development in Chicago is to have the muscle as a general interface by surgically redirecting nerves into accessory muscles. So if you have an amputation which is high and implies that the nerve, for example, innervating hand movement is cut, then you can surgically take this nerve and send it to another muscle. The nerve will reinnervate that muscle, and now we use this muscle that we reinnervate as a bioscreen of the nerve activity. So it's a biological connector to the nerve. So this muscle now becomes a bioscreen of the nerve activity, and by the techniques that I explained to you, then you can get the firings of activity from the motor neurons running through the nerve. And in this way, you have a very general neural interface. You can take any nerve, in principle all the nerves innervating the hand and the arm, reinnervate them in muscles that you have available, use those muscles as biological amplifiers of nerve activity, probe them with EMG, high-density EMG. It can be invasive for a full long-term application so that it's all implanted, or non-invasive at the moment for the developments. And then you have a motor neuron decoding, and then from the motor neuron decoding you can rebuild the prosthetic control in a natural way. So we actually did that, and we proved that we can do that. We proved this very recently, although we proved it offline. And this is a patient, data from a patient, a relatively high-level amputee who underwent through this reinnervation procedure. So we had surgically, together with the Medical University of Vienna, redirected nerves into accessory muscles, basically all the main nerves controlling the missing arm. And then we had EMG probing, non-invasive at the moment, for laboratory developments, but the same concept can then be translated into an invasive product. And then we had the decoding of motor neuron pools. So each nerve activity was decoded through the reinnervation points, and you can see them here. And then we had a multi-scale biomechanical model that, from the motor neuron pool, reconstructed the muscle tendon unit forces for each muscle tendon unit, and this was projected into joint moment forces. This is an example of elbow forces and wrist and forearm forces. And here you can see in this example a validation of the output from the man-machine interface, starting from motor neurons. And the gold standard to compare in this case is the contralateral limb. So the patient was asked to do mirror movements, and we use the contralateral limb as to validate the estimates. Of course, it's not the ideal validation, but since the limb is missing, you cannot have another type of validation. So the interesting thing here is that these estimates of joint moments that can control a prosthetic limb in the future have been done entirely from the motor neuron decoding obtained in the way I described. So we have a spinal interface that estimated the biomechanics of a missing limb. So that is a viable solution. It can be done, and it can be done clinically. Of course, the next steps will be to have this online and to have this in the future, potentially with everything implanted. So I finished what I wanted to share with you today. I have, as a conclusion, I show you the same summary slide that you have seen a few times now. So I have discussed with you some of the challenges of interfacing robots with humans. I have specifically addressed the prosthetic field, but similar problems arise when you think in a number of other rehabilitation technologies, for example, exoskeletons or orthosis, or even robots that you use for therapy in hospitals. You still have the need of a man-machine interface. I've then described some of the state-of-the-art myoelectric control using the classic EMG, and then to give you an example how high-density EMG, that was one of the main topics this morning, could push the field, in this case the prosthetic field, further. I've shown you how from the classic myocontrol, which is gross interference EMG, we may go to a potentially much more detailed type of interface with a direct motor neuron interface. And with this, I thank you very much for the attention.